Imagine a future where creating almost any molecule you can conceive. Maybe life-saving drugs, maybe revolutionary new materials. Imagine it's no longer this painstaking trial and error thing, but an intelligent, precise act of engineering. Sounds pretty futuristic, right? Like something out of a lab way down the line. Well, that future might actually be closer than you think.
It really might, yeah. Today we're doing a deep dive into a concept that sounds, well, groundbreaking. It's called quantum-correlated synthesis, QCS for short. And our mission here is really to unpack this idea. It's potentially paradigm shifting. We want to look at its core components, figure out how it's supposed to work, and look at the radical implications. For chemistry, yes, but maybe even beyond.
And what I find fascinating here is that the person proposing this, Shahryar Ghiasi, isn't necessarily from a traditional chemistry background. He's described as an Iranian enthusiast of science, tech, philosophy, with experience in architecture and city management. So this isn't just like a small step forward.
No, not at all.
It sounds like a whole new way of thinking, a conceptual leap, really. It could fundamentally change how we interact with molecules. So yeah, let's unpack it.
Okay, so at its heart, QCS is really a direct response to some of chemistry's biggest, most persistent challenges. Things like sustainability, efficiency, and, crucially, being able to predict what's actually going to happen in a reaction. Right now, a lot of chemistry is, well, let's call it statistical, probabilistic. You mix stuff together, you heat it, you stir it, you sort of hope the molecule you want forms. Often you get a lot of other stuff too. Byproducts, waste.
Right. It reminds me of that analogy, like trying to build complex IKEA furniture blindfolded. You just throw all the pieces on the floor hoping they click together, and you end up with, leftover screws and maybe a wobbly table.
Oh,
Worse.
that's a pretty good analogy, actually, yeah.
Yeah.
You're relying on random collisions, bulk conditions like temperature and pressure. QCS flips that script. It aims for a deterministic model. Total control. The core idea is using real-time quantum computations, basically predicting quantum behavior on the fly to guide the precise manipulation of molecules while they're reacting, all happening within a very dynamically controlled environment.
Okay, so guiding the molecule.
Exactly. It's about bridging that gap between purely theoretical prediction and what we can actually make in the lab, the goal. Near-perfect selectivity, making only what you want, minimal waste. And the ability to create really complex molecules on demand. It's like upgrading from just, shaking the box and hoping to having this molecular GPS that guides every piece precisely into place.
Wow, that's a huge shift from
No,
chance
no.
to absolute control almost. And to achieve this, you mentioned QCS relies on three core technologies, three pillars you called them. The first one being quantum mechanical simulation, the digital twin for molecules. What does that mean? How does it see the future?
Yeah, the digital twin. This is essentially the predictive brain of the whole system. And it goes way beyond current AI or machine learning, which mostly learn from past data. This uses ab initio methods, meaning from first principles, things like advanced density functional theory. It's about solving the fundamental physics equations directly, like the Schrödinger equation, which describes how electrons behave in molecules. So it creates this dynamic digital twin that's constantly mapping the entire potential energy surface of the reaction. Basically, all the possible states and paths the molecules could take in real time.
Okay, so not just predicting the final outcome, but literally seeing every possible twist and turn as it happens. But hang on, these quantum calculations, they take massive computing power, right? How close are we really to doing that in real time for, say, a complex drug molecule? Is that feasible now or still mostly theory?
That's the key question, and it's becoming more feasible. The simulation doesn't just predict the desired path. It anticipates the wrong turns, side reactions, energy barriers, these things called kinetic traps before they happen. This foresight allows the system to intervene proactively. And you're right, traditionally these calculations are incredibly intensive, hours, days, even weeks. But things are changing fast. We're seeing specialized hardware, custom supercomputers, and of course the whole field of quantum computing is maturing rapidly. So getting these simulations down to the time scale of an actual chemical reaction, milliseconds, maybe seconds is looking plausible. It's a major research focus right now.
Okay, that's crucial. So the brain is becoming fast enough. Then pillar two is the adaptive reaction environment, the molecular sculptor. This is where the actual physical chemistry happens, the shaping.
Exactly. This is the physical setup, the hands of the system, if you like.
Yeah.
It's probably going to be based on advanced microfluidics, or maybe even nanofluidics. Think of tiny channels, smaller than a human hair, where you have exquisite control over minuscule volumes of reactants. And embedded within this reactor, you have a whole suite of active manipulators, tools to interact with the molecules.
What kind of tools? How do you physically nudge a molecule? That sounds incredibly delicate.
It is. We're talking things like femtosecond laser pulses. These are ultra-short bursts of light, precisely tuned. You can use them to inject energy into a specific vibration within a molecule, like targeting one specific bond to make it easier to break exactly where you want. That's called mode-selective chemistry. Then you have phased electromagnetic fields. These can be used to, say, orient molecules the right way before they react, or stabilize those really fleeting high-energy transition states.
Ah, those unstable intermediates.
Precisely. Stabilizing them can make a difficult reaction suddenly much easier. You can even influence electron spins sometimes. And then there are acoustic transducers, high-frequency sound waves. These can create tiny pressure gradients or even cavitation bubbles, little imploding bubbles that release focused mechanical energy, useful for mixing or breaking things apart gently.
Wow. So you've got lasers, fields, sound waves, all precisely controlled based on what the quantum simulation predicts is needed at that exact moment, nudging molecules along the right path. It sounds incredibly precise. But I wonder, does that level of control mean we lose the element of surprise? You know, those happy accidents in traditional chemistry that sometimes lead to unexpected discoveries. Can QCS account for serendipity?
That's a really interesting philosophical point, actually. QCS is definitely geared towards deterministic creation, making exactly what you set out to make, minimizing randomness. Those serendipitous discoveries often arise precisely because traditional chemistry is so probabilistic. You stumble onto things. QCS aims to remove that stumbling. But by giving us such deep understanding and control, it might let us design entirely new reaction pathways, things we'd never find by chance. So it's maybe a different kind of discovery. And Pillar 3 helps lock in that precision even more. That's dynamic supramolecular templating. We call it the molecular assembly line.
Molecular assembly line. Okay, so how does that work? Is it like a tiny physical mold?
Sort of, yeah. It involves designing these special molecular structures, could be like cages or synthetic mimics of enzymes or specially treated surfaces. They're held together by weaker bonds, non-covalent bonds, kind of like molecular Velcro. They can grab onto molecules and let them go when triggered. And their main job is to solve the entropy problem.
The entropy problem,
Right.
right? The fact that molecules are just bouncing around randomly all the time.
It's exactly that. For two molecules to react properly, they usually need to collide in a very specific orientation. Just bumping into each other isn't enough. In a normal solution, getting that perfect alignment is mostly just luck, probability. These templates, they pre-organize the reactant molecules. They hold them in the perfect position relative to each other. This massively increases the chance of the desired reaction happening right off the bat. Then, once the reaction is done, you apply another stimulus, maybe a change in light or pH, and the template releases the product, ready for the next cycle.
Okay, I think I'm getting the picture. You've got the brain, the quantum simulation predicting the path. You've got the hands, the adaptive reactor with its lasers and fields actually doing the nudging. And you've got the assembly line, the templates holding everything in place to start with. So let's walk through it. Say we want to make a complex drug molecule using QCS. How does it unfold?
Okay, step 1, initialization. Your starting reactant molecules are introduced into the reactor. They get captured in position by those supramolecular templates, lined up perfectly.
Got it. And then the quantum prediction brain kicks in immediately.
Instantly, the system starts running those real-time quantum calculations. It maps out the most efficient, lowest energy pathway to get you to that final drug molecule. And, just as importantly, it identifies potential wrong turns, side reactions that could make impurities or energy barriers that might stop the reaction.
Right. And that's the cue for the dynamic control, the hands, to get involved.
Yes. Based on those constantly updating predictions from the quantum brain, the reactor's control systems activate, the lasers, the fields, the acoustic waves. And these aren't just switched on, they're precisely modulated. Maybe a specific laser pulse zaps a particular bond to weaken it at the right moment. Or maybe an electromagnetic field flickers on to stabilize that tricky transition state just as the molecules pass through it. It's all timed perfectly to guide the molecules along that optimal path.
And it's not just set and forget, right? You mentioned feedback. What if something starts to go slightly off course?
Absolutely critical. There are sensors embedded in the system, constantly monitoring the state of the molecules. Non-invasively, ideally. That real-time data feeds straight back into the quantum simulation. The simulation refines its predictions based on what's actually happening and adjusts the instructions to the reactor controls. It's a continuous closed-loop feedback system. Self-correcting, intelligent chemistry. And then finally, once the sensors confirm the target drug molecule is formed, the template gets the signal to release it. It's collected, and the system resets, ready for the next batch.
That is just fundamentally different from how we think about making things chemically now. So let's talk about the big picture. Why is this QCS idea considered such a potential game changer? What problems does it solve?
Well, it hits some really fundamental challenges head-on. First, sustainability. This is huge. By aiming for near-perfect selectivity, you essentially eliminate byproducts. That means drastically less chemical waste.
Yeah.
You approach what chemists call 100% atom economy. Nearly every atom you put in ends up in your product. Think of the environmental impact reduction. Plus, using targeted energy like lasers instead of just heating everything up means much lower energy consumption. And you could potentially get rid of hazardous solvents, maybe even use feedstocks like Kuro or methane directly. It's the ultimate vision of green chemistry.
Okay, ultimate green chemistry, that alone is massive. What about just making things better, faster, more efficiently?
That's the other side of the coin. Efficiency and selectivity. QCS promises to crack the code on controlling exactly which molecule you make, especially when there are many possibilities. This would let us produce really intricate molecules, complex drugs, advanced materials, much more efficiently and cheaply than we can now. Less waste means less purification needed, which saves time and money. And think about R&D. If you can reliably make what your theory predicts, you could slash drug or material development times from years down to maybe weeks. That speeds up innovation incredibly.
And you also mentioned making things that are currently just impossible.
Yes, that's the prediction and control aspect. Because the quantum prediction isn't just passive, it's an active part of the synthesis, guiding it. This could open the door to creating molecules that are just too complex or too unstable to make with current methods. Maybe they fall apart too quickly, or the reaction pathways are just too convoluted. QCS offers unprecedented control right down to the stereochemistry, the exact 3D arrangement of atoms, which is critical for things like drugs. We could potentially design and build completely new classes of molecules with functions we haven't even imagined yet.
This is where it gets really exciting for everyone, right? The potential real-world applications. If this works, what could it mean for us? Let's start with medicine.
Oh, the implications for pharma and medicine are profound. Imagine on-demand personalized medicine. Truly bespoke drugs, synthesized for your specific cancer variant, maybe in hours, right there at the clinic or hospital. Or think about antibiotic resistance. We could potentially design and synthesize new antibiotics much faster, responding to emerging superbugs almost in real time, and complex natural products like the anti-cancer drug Taxol. It's currently really hard and expensive to get. QCS could make it efficiently. Even things like short-lived radiopharmaceuticals for P teams. You could potentially make those on-site just before they're needed, improving diagnostics.
Personalized drugs, rapid antibiotics. That's transformative for health. What about building things, material science, manufacturing?
Huge potential there, too. You could construct essentially perfect, defect-free semiconductors or polymers for next-gen electronics. Imagine flawless computer chips every time. Or designing and building metamaterials atom by atom. These are materials engineered to have properties not found in nature, maybe for advanced optics, super strong lightweight composites. You could even potentially create self-healing materials. Imagine a phone screen or a car part that just repairs its own cracks. QCS could build the complex structures needed for that.
Self-healing materials, that sounds like pure science fiction becoming reality. And energy and sustainability, those are massive global challenges.
Absolutely critical areas. QCS could let us design and manufacture vastly better catalysts. For example, catalysts to efficiently convert captured Kuros into useful fuels or chemicals tackling climate change directly. Perhaps one of the biggest impacts could be sustainable fertilizer. Making ammonia from atmospheric nitrogen currently uses the Haber-Bosch process, which is incredibly energy intensive, responsible for like 1 to 2% of global energy use. QCS might enable doing that fixation at room temperature, mimicking nature, which would be revolutionary. And also, better catalysts for splitting water using sunlight to produce clean hydrogen fuel. And it's really green energy cycle.
Wow. Replacing Haber-Bosch. And even agriculture and food.
Yeah, precision matters there too. Think about producing pesticides that are ultra-targeted. Lethal only to the specific pest insect, but completely harmless to beneficial ones like bees or to us. Or synthesizing complex, maybe rare flavor and fragrance molecules on demand. Instead of relying on extracting them from limited natural sources, you could just make them. More sustainable, more consistent.
Okay, this vision is, well, it's staggering. It touches almost every aspect of technology and industry, but it also sounds incredibly difficult to actually build. What are the big hurdles? What's the road ahead to make QCS a reality?
It's definitely a grand challenge. There are several major hurdles. First is bridging the timescale gap. Those quantum simulations need to be fast. orders of magnitude faster than they are now for complex systems. They need to run in milliseconds or seconds and be
Yeah.
perfectly synced up with the physical response time of the reactor components, the lasers, the fields. That synchronization is key.
Yeah.
Then there's high-fidelity sensing. You need sensors that are incredibly sensitive, can see what's happening at the molecular level in real time, and do it without disturbing the reaction itself. Measuring quantum states non-invasively is hard.
Right. You can't control what you can't measure accurately. And the software, the control system itself.
That's another huge one. Control algorithm development. You need extremely sophisticated software to translate the predictions from the quantum simulation into precise, timed instructions for all those manipulators in the reactor. It's basically creating a whole new field of quantum control theory, specifically for chemical synthesis, building the operating system for molecular creation, really. Finally, there's the sheer integration engineering challenge, putting it all together. A quantum computer, or at least a very powerful classical one, tightly coupled to a microfluidic reactor packed with lasers, coils, sensors, and the supramolecular chemistry. Getting all that to work together reliably in one instrument. That's a systems engineering task on the scale of building, say, a particle accelerator or maybe even a fusion reactor. It's monumental.
Monumental, yeah. So it's clear that quantum correlated synthesis, QCS, isn't just a small improvement. It really is a potential conceptual leap. It reframes making molecules not as mixing and hoping, but as an active, intelligent, deterministic act of engineering. It truly could revolutionize our world, molecule by molecule.
It absolutely could, and it leads to some pretty profound questions, doesn't it? If we really do gain this kind of power, the ability to design and create basically any molecule we can imagine with near-perfect precision, what are the ethical considerations? What are the societal implications of that kind of control over matter? How does shifting from just discovering what nature already made to actively engineering almost anything at the molecular level, how does that fundamentally change our relationship with the world around us?
That is definitely something to think about. A powerful question to ponder as this incredibly exciting field hopefully continues to develop.